There is something out there that we cannot see. It does not glow. It does not reflect light. It passes through walls and through you and through entire planets without leaving a trace. And yet this invisible something makes up most of the matter in the entire universe. Without it, you would not exist. The Earth would not exist. The sun, the stars, the galaxies, none of it would be here. Everything you have ever seen, everything you have ever touched, every person you have ever loved, all of it owes its existence to something we have never directly observed and still do not fully understand. This is the story of dark matter. For most of human history, we assumed that what we could see was all there was. The stars above us, the ground beneath our feet, the air we breathed, these were the building blocks of reality. When scientists first began measuring the universe with precise instruments, they expected to find more of the same. More stars, more gas, more dust. What they found instead was a mystery so profound that it has consumed the lives of thousands of researchers for nearly a century. The universe, it turns out, is mostly invisible. Consider the numbers for a moment. For every atom of ordinary matter in the cosmos, there are roughly 5 times as many particles of dark matter. The hydrogen and helium that make up most stars, the carbon and oxygen in your body, the iron at the Earth's core, all of this visible matter is the minority. The majority is something else entirely, something that has never been captured in a laboratory or seen through any telescope. The sun, as massive as it seems to us, is nothing compared to the dark matter surrounding it. Our entire solar system sits within the Milky Way's dark matter halo, embedded in a vast structure that extends far beyond the visible disk of stars. The visible galaxy we photograph and admire is just the glowing center of something much larger. We call it dark matter because we do not know what else to call it. The name is not particularly accurate. It is not dark in the way that a shadow is dark, or the way that space appears dark when you look up at night. Those things are simply the absence of light. Dark matter is something else entirely. It is matter that exists outside the electromagnetic spectrum completely. Photons pass through it. Radio waves pass through it. X-rays, gamma rays, infrared, all of them continue on their way as if the dark matter were not there. This creates an interesting problem. Nearly everything we know about the universe we know because of light in some form. We see the sun because visible light from its surface reaches our eyes. We detect distant galaxies because their light has traveled billions of miles to reach our telescopes. We know what stars are made of because of the specific wavelengths they emit. Our entire toolkit for studying the cosmos relies on electromagnetic radiation. So how do we know dark matter exists at all? The answer comes down to gravity. While dark matter refuses to interact with light, it cannot hide from gravity. Every bit of matter in the universe, visible or not, pulls on every other bit of matter. This is the law of gravitation that Isaac Newton first described in 1687. The more mass something has, the stronger its gravitational pull. And when scientists started carefully measuring how things move in the universe, they found that nothing was moving the way it should. The discovery did not happen all at once. It came in pieces, spread across decades, with different scientists stumbling upon the same impossible conclusion from entirely different directions. The first hints appeared in the 1930s, but almost nobody paid attention. More clues emerged in the 1970s and 1980s. By the 1990s, the evidence had become overwhelming. Something massive was out there, and we could not see it. Let me take you back to the beginning, to a time when the universe seemed simpler, when the biggest questions in astronomy were about distances and compositions, not about invisible matter that defies explanation. Let me show you how we went from confident ignorance to confused enlightenment. And let me explain why this invisible substance matters so much, not just to scientists in laboratories, but to you right now in this very moment. Because here is the remarkable truth. The visible universe, everything you can see with your eyes or with any telescope ever built, makes up only about 5% of what actually exists. The rest is hidden. About 27% is dark matter. The remaining 68% is something even stranger called dark energy, which is a topic for another time. For now, let us focus on that 27%. Let us talk about the invisible scaffolding upon which all of reality is built. The story begins in 1933, in a place called the California Institute of Technology. A Swiss astronomer named Fritz Zwicky was studying a collection of galaxies known as the Coma Cluster. This is a massive group of over 1,000 galaxies located about 320 million light-years from Earth, which is roughly 1.9 sextillion miles away. Zwicky was trying to measure how fast the galaxies in this cluster were moving. To understand what Zwicky was doing, you need to know a bit about how astronomers measure the motion of distant objects. When a galaxy is moving toward us, the light it emits is compressed, shifting toward the blue end of the spectrum. When it is moving away, the light is stretched, shifting toward the red. This is called the Doppler effect. And it is the same reason an ambulance siren sounds higher-pitched when approaching and lower-pitched when receding. By measuring these color shifts in the light from galaxies in the Coma Cluster, Zwicky could determine how fast each galaxy was moving relative to the cluster as a whole. Some were approaching, some were receding, as they orbited around the center of mass of the entire cluster. Zwicky was a meticulous observer. He had access to the 18-inch Schmidt telescope at Palomar Observatory, one of the best instruments of its time. He photographed the Coma Cluster repeatedly, measured the positions and spectral shifts of the galaxies, and began his calculations. You might wonder why the speed of distant galaxies matters. The answer has to do with gravity and orbits. Think about our own solar system. The planets orbit the Sun because the Sun's gravity pulls on them. The closer a planet is to the Sun, the faster it needs to move to avoid falling inward. Mercury, the closest planet, zips around the Sun at about 112,000 miles per hour. Neptune, way out at the edge of the solar system, moves at only about 12,000 miles per hour. The relationship between distance and speed tells us about the mass at the center doing the pulling. Zwicky was trying to apply this same logic to the Coma Cluster. By measuring how fast the galaxies were moving, he could calculate how much mass the cluster contained. More mass means more gravity, which means the galaxies would be moving faster. It was straightforward physics. Except the numbers did not add up. When Zwicky measured the speeds of the galaxies, he found they were moving much too fast. Way too fast. Based on how quickly they were orbiting around the center of the cluster, the Coma Cluster would need to contain about 400 times more mass than what he could see. If the only mass in the cluster was the visible galaxies, their gravity would be far too weak to hold everything together. The galaxies should have been flying apart, scattering into the void like shrapnel from an explosion. But they were not flying apart. The cluster was stable. It had been stable for billions of years. Something was holding it together, and that something was invisible. Zwicky called this mysterious Massdunkel Materie, which is German for dark matter. He proposed that the cluster must be filled with some kind of matter that did not emit light, matter that could only be detected through its gravitational effects. It was a bold claim, and almost nobody believed him. Part of the problem was Zwicky himself. He was brilliant, but abrasive. He called his colleagues at Caltech spherical idiots, meaning they were idiots no matter which direction you looked at them from. He was not good at making friends or building alliances in the scientific community. When he published his dark matter findings, many astronomers simply ignored him. Others assumed he had made a measurement error somewhere. The idea that most of the matter in a galaxy cluster could be invisible seemed absurd. And so, the concept of dark matter sat largely forgotten for nearly 4 decades. The next chapter in this story takes us to the 1970s and to a scientist who approached the problem from an entirely different angle. Her name was Vera Rubin, and she was studying something much closer to home than distant galaxy clusters. She was measuring how stars move within individual galaxies. Rubin worked at the Carnegie Institution in Washington, D.C., alongside an instrument maker named Kent Ford. Together, they had built an extremely sensitive spectrograph, a device that could measure the precise speeds of stars by analyzing the light they emitted. They pointed their instrument at the Andromeda Galaxy, the nearest large galaxy to our own Milky Way, located about 2.5 million light-years away. Here is what Rubin expected to find. Galaxies, like solar systems, have most of their visible mass concentrated in the center. When you look at a spiral galaxy, you see a bright bulge in the middle, where most of the stars are clustered. The outer edges of the galaxy are much more sparse, with fewer stars and less mass. Based on this distribution, Rubin expected the stars at the outer edges of Andromeda to be moving slowly, just like Neptune moves slowly at the outer edge of our solar system. Instead, she found that the outer stars were moving just as fast as the inner ones. This made no sense. It violated the basic physics of orbits that had been understood since Newton's time. If the only mass in Andromeda was the visible stars, gas and dust, then the outer stars should have been moving much more slowly. They were too far from the gravitational center to be moving so fast. At those speeds, they should have been flung out of the galaxy entirely, like water droplets flying off a spinning bicycle wheel. Rubin checked her instruments. She checked her calculations. She observed other galaxies. Everywhere she looked, the same pattern emerged. The outer regions of galaxies were rotating too fast. Something was providing extra gravitational pull, something that could not be seen. Unlike Zwicky, Rubin had the advantage of extensive, careful data and a more receptive scientific community. Her measurements were precise and repeatable. Other astronomers began conducting similar observations and found the same results. Galaxy after galaxy showed this impossible rotation pattern. The conclusion was inescapable. Galaxies must be embedded in vast halos of invisible matter, matter that extends far beyond the visible stars and provides the extra gravity needed to hold everything together. The dark matter is not concentrated in the center where we can see the stars. It forms a huge spherical cloud that surrounds the entire galaxy, stretching millions of light-years in every direction. Think of it like this. Imagine a galaxy is a dinner plate sitting on a table. The visible stars, the ones we can see through our telescopes, are like the food arranged on the plate. But the plate itself, the thing holding everything together and giving it structure, is invisible. The dark matter is the plate. Without it, the food would just be scattered across the table with nothing to contain it. Vera Rubin's story is worth pausing on because she faced obstacles that had nothing to do with physics. When she applied to graduate school at Princeton in 1948, she was rejected. Not because she lacked qualifications, but because Princeton did not admit women to its astronomy program. That policy did not change until 1975. Rubin went to Cornell instead, and then to Georgetown, where she earned her doctorate while raising 4 children. Throughout her career, she worked in a field dominated by men. She was often the only woman at conferences. She was denied access to certain telescopes because of her gender. When she applied to observe at Palomar Observatory in California, one of the premier observing sites in the world, she was initially turned down because the facility had no women's restroom. She persisted anyway, and her persistence changed our understanding of the universe. Rubin received many honors later in life, including the National Medal of Science in 1993, but she never received the Nobel Prize, despite making a discovery that was arguably as significant as many that did receive that honor. She died in 2016 at the age of 88. The Vera C. Rubin Observatory in Chile is named in her honor. Her story reminds us that science is a human endeavor. The people who make discoveries are not abstract figures in textbooks. They are real individuals with struggles and triumphs, facing obstacles both cosmic and personal. The discovery of dark matter was made by people like Zwicky and Rubin, each with their own quirks and challenges, each contributing pieces to a puzzle that remains unsolved. By the early 1980s, the astronomical community had largely accepted that dark matter was real. The evidence from galaxy rotation curves was simply too strong to ignore. But acceptance brought new questions. What exactly was this dark matter? Where did it come from? And how could we ever hope to study something we cannot see? Before we explore what dark matter might be, let us first understand what it does. Because even though we cannot see dark matter directly, we can see its effects everywhere we look. And those effects are not subtle. Dark matter has shaped the entire structure of the universe. Imagine the early cosmos, just a few 100,000 years after the Big Bang. The universe was almost perfectly smooth. Matter was spread out nearly evenly in all directions, with only tiny variations in density from one region to another. These variations were minuscule, differences of perhaps 1 part in 100,000. But they were enough. We know about these tiny variations because we can see them. The cosmic microwave background, the afterglow of the Big Bang, carries the imprint of these early density fluctuations. When the Planck satellite mapped the microwave sky with unprecedented precision, it revealed hot and cold spots corresponding to regions that were slightly denser or slightly less dense in the early universe. These spots are the seeds of all the structure we see today. In regions where the density was slightly higher, gravity began to pull matter inward. The denser regions attracted more matter from their surroundings, which made them even denser, which attracted even more matter. Over hundreds of millions of years, this process amplified those tiny initial fluctuations into something dramatic. This process is called gravitational instability, and it is the engine that built the cosmic web. Small differences in density grew larger over time, like a snowball rolling downhill and gathering more snow. Eventually, the densest regions collapsed into galaxies, while the less dense regions became the voids we see today. But here is the problem. If the universe contained only ordinary matter, this process would have taken far too long. The regular matter in the early universe was still hot and energetic, bouncing around and resisting the pull of gravity. It was like trying to collect a pile of bouncing rubber balls while they are still in motion. The expansion of the universe would have spread everything too thin before gravity could pull enough ordinary matter together to form galaxies. Dark matter solved this problem. Unlike ordinary matter, dark matter does not interact with light. This means it was not affected by the intense radiation that filled the early universe. While ordinary matter was being pushed around by photons, dark matter was quietly settling into clumps, pulled together by its own gravity. These dark matter clumps formed the seeds around which galaxies would later grow. By the time the universe cooled enough for ordinary matter to stop bouncing around, the dark matter scaffolding was already in place. Ordinary matter simply fell into the gravitational wells that dark matter had prepared. The hydrogen and helium gas accumulated in these wells collapsed under gravity and ignited into the first stars. This means that every galaxy you see in the night sky, including our own Milky Way, formed inside a pre-existing structure of dark matter. We call these structures dark matter halos. The visible galaxy is just the luminous core of something much larger and almost entirely invisible. To understand the scale of these halos, consider our own Milky Way. The visible part of our galaxy, the disk of stars that you can see on a dark night, is roughly 100,000 light-years across. That is about 588 quadrillion miles from one edge to the other. It seems enormous, but the dark matter halo surrounding the Milky Way extends much farther. Estimates suggest it reaches out to about 1 million light-years or more, perhaps 10 times the diameter of the visible disk. Inside this vast invisible sphere, the stars and gas of the Milky Way are just a small, bright core. We are embedded in dark matter, the way a yolk is embedded in an egg white. The dark matter extends above and below the galactic disk, in front of us and behind us, in every direction. And here is a remarkable fact. The dark matter halo of the Milky Way has a mass of roughly 1 to 2 trillion times the mass of the Sunday, the visible matter in our galaxy. All the stars and gas and dust adds up to only about 100 billion to 400 billion solar masses. That means the dark matter outweighs the visible matter by a factor of 5 or 10 to 1. When you look up at the night sky and see the stars of the Milky Way, you are seeing less than 20% of what is actually there. The rest is invisible. Computer simulations have allowed scientists to model this process in extraordinary detail. By programming the laws of gravity and the known properties of dark matter into supercomputers, researchers can simulate how the universe evolved over billions of years. These simulations start with the tiny density fluctuations we see in the cosmic microwave background, the leftover light from the early universe, and then fast forward through cosmic time. The first such simulations were run in the 1980s, using the most powerful computers of the day. They could only track a few thousand particles, representing clumps of matter far larger than individual galaxies. Yet even these crude simulations showed something remarkable. A universe that started almost perfectly smooth naturally evolved into one with structure, with dense regions connected by filaments and separated by voids. As computers grew more powerful, simulations grew more detailed. The Millennium simulation, completed in 2005, tracked over 10 billion particles and followed the evolution of a box of the universe about 2 billion light-years on a side. It showed the formation of individual galaxies, the growth of galaxy clusters, and the emergence of the cosmic web in stunning detail. More recent simulations like Illustris TNG and Eagle have added even more physics. They include not just dark matter, but also ordinary matter, with gas dynamics, star formation, supernova explosions, and black hole growth, all modeled self-consistently. These simulations produce virtual universes that are nearly indistinguishable from our own. The results are striking. Galaxies form in the right places. They cluster together in the right patterns. They have the right shapes and sizes and rotation speeds. When the simulations are run without dark matter, everything falls apart. The galaxies do not form properly. The universe looks nothing like what we observe. These simulations also make predictions. They tell us how dark matter should be distributed on small scales around individual galaxies and on large scales across the cosmic web. These predictions can be tested against observations, providing another way to check our understanding of dark matter. This is one of the strongest pieces of evidence for dark matter. It is not just that we see its gravitational effects in individual galaxies and galaxy clusters. It is that dark matter is essential for explaining how the entire universe came to look the way it does. Without it, the cosmos would be a formless void. Let me paint a picture of the large-scale structure of the universe, because this is where dark matter's influence becomes truly cosmic in scope. If you could zoom out far enough, far beyond our galaxy, far beyond our local group of galaxies, far beyond the nearest superclusters, you would see something remarkable. The universe is not random. It is not a uniform distribution of galaxies scattered evenly through space. Instead, it has structure, a pattern that spans billions of light years. Scientists call this pattern the cosmic web. It is a network of filaments, walls, and nodes, all connected like an impossibly vast three-dimensional spiderweb. The nodes are clusters of thousands of galaxies, massive concentrations of matter where the filaments intersect. The filaments themselves are long, thin structures stretching hundreds of millions of light years, like the threads connecting the knots in a net. Between the filaments are voids, enormous empty regions that contain almost nothing at all. Some of these voids are astonishing in their emptiness. The Boötes void, discovered in 1981, is about 330 million light-years across. That is roughly 2 sextillion miles of almost pure nothing. If you were floating in the center of the Boötes void and looked out in any direction, you would see darkness. The nearest galaxy would be over 100 million light-years away. It would be one of the loneliest places in the entire universe. The cosmic web is not made of visible matter. Most of it is dark matter. The galaxies we see are just the tips of the icebergs, bright points of light tracing out a much larger invisible structure. When scientists create maps of the dark matter distribution in the universe, they find that it matches the distribution of galaxies almost perfectly. Where the dark matter is densest, that is where the galaxies are. Where the dark matter is sparse, the galaxies are sparse too. This relationship is not coincidental. The galaxies are where they are because the dark matter put them there. Over billions of years, dark matter's gravity gathered ordinary matter into the dense regions, while the voids became emptier and emptier. The cosmic web is literally the skeleton of the universe, and dark matter is the bone. To map the cosmic web, astronomers have conducted massive surveys that catalog the positions of millions of galaxies. One of the most ambitious was the 2-degree field galaxy redshift survey, completed in 2002, which mapped over 200,000 galaxies. Its results confirmed what simulations had predicted. Galaxies are not scattered randomly through space. They cluster along filaments and around nodes separated by vast, empty regions. The surveys have grown larger over time. The Sloan Digital Sky Survey, which began in 2000, has measured the positions of over 1 million galaxies. It revealed the cosmic web in unprecedented detail, showing filaments that stretch for hundreds of millions of light years and voids that span hundreds of millions of light years across. More recently, the Dark Energy Survey, completed in 2019, used a different technique to map the dark matter directly. Instead of just counting galaxies, It measured how light from distant galaxies is slightly distorted by the gravitational pull of intervening dark matter. By carefully analyzing these distortions across a large fraction of the sky, researchers could reconstruct where the dark matter is located. The picture that emerges is awe-inspiring. The universe is organized into a foam-like structure with dense nodes connected by thin filaments surrounding enormous empty voids. This structure spans the entire observable universe, a pattern repeated on scales of billions of light years, and nearly all of it is invisible. The galaxies we see are just the illuminated tips of a vast, dark structure. Recent surveys have allowed us to map this structure in unprecedented detail. The Sloan Digital Sky Survey, which began in 2000, has measured the positions of over 1 million galaxies. The Dark Energy Survey, completed in 2019, used a different technique to map the dark matter directly by measuring how its gravity bends light from distant sources. These maps reveal the cosmic web in stunning clarity, showing filaments and voids that stretch across billions of light years. What these maps tell us is that the universe is organized. It has architecture, and that architecture is written in dark matter. Speaking of bending light, this brings us to one of the most powerful tools we have for studying dark matter: gravitational lensing. You may have heard that gravity bends light. This is one of the predictions of Einstein's general theory of relativity, published in 1915. Einstein showed that massive objects warp the fabric of space-time around them. Light traveling through this warped space-time follows a curved path rather than a straight line. The effect is similar to looking through an old glass window, where imperfections in the glass distort the view of what is on the other side. When light from a distant galaxy passes near a massive object like a galaxy cluster, it gets bent. If the geometry is right, the massive object acts like a lens, magnifying and distorting the image of the distant galaxy. This is called gravitational lensing. There are different types of gravitational lensing, depending on the strength of the effect. Strong lensing occurs when a very massive object is almost directly between us and a distant source. In these cases, the background source can be stretched into arcs or even split into multiple images that appear in different positions around the lens. Some of the most spectacular astronomical images ever taken show these gravitational arcs, thin smears of light curved around massive galaxy clusters. The first gravitational lens was discovered in 1979 when astronomers noticed that a quasar appeared to have a twin. The two images were remarkably similar, with the same brightness, the same spectrum, and the same pattern of variability. It turned out they were not two separate objects, but two images of the same quasar, split by the gravity of a galaxy between us and the quasar. Since then, hundreds of strong gravitational lenses have been discovered. Some show spectacular arrangements of multiple images arranged in crosses or rings around the lens. The geometry of these images tells us about the distribution of mass in the lensing object. Weak lensing is more subtle. It occurs when light from distant galaxies is slightly distorted by the combined gravity of many less massive objects along the line of sight. The distortion is tiny, just a few % change in the apparent shape of each background galaxy. But by measuring this distortion across thousands or millions of galaxies, astronomers can reconstruct the invisible mass causing the bending. Weak lensing has become one of the most powerful tools for mapping dark matter on large scales. Because it responds to all mass, whether visible or not, it directly reveals the distribution of dark matter. The technique requires precise measurements of galaxy shapes across large areas of sky, which is why modern surveys like the Dark Energy Survey have invested so much effort in careful image analysis. Now, Here is where things get interesting. The amount of bending depends on how much mass is doing the lensing. More mass means more bending. By carefully measuring how light from background galaxies is distorted as it passes through a foreground cluster, astronomers can calculate exactly how much mass that cluster contains. When they do this, they find the same result that Zwicky found nearly a century ago. The clusters contain far more mass than what we can see. The gravitational lensing reveals invisible mass, dark matter that is bending the light but not producing any light of its own. Gravitational lensing has become one of our most important tools for mapping dark matter. By analyzing the distortion of thousands of background galaxies, scientists can create detailed maps of where the dark matter is located within clusters. These maps show that the dark matter forms enormous clouds, much larger than the visible galaxies, with the galaxies embedded within them like raisins in a pudding. In 2006, astronomers used gravitational lensing to study one of the most important objects in the dark matter story, the bullet cluster. The bullet cluster, officially known as 1E0657-558, is located about 3.7 billion light-years from Earth in the constellation Carina. It gets its nickname from its distinctive shape. One of the two colliding clusters has a bullet-like appearance with a sharp front edge where gas has been compressed by the collision. The bullet cluster is actually two galaxy clusters that collided with each other about 150 million years ago. This might sound like a dramatic event, and in some ways it was. But galaxy cluster collisions are not like car crashes. The individual galaxies within the clusters are so far apart that they mostly pass by each other without colliding. It is the gas between the galaxies that slams together. Galaxy clusters contain enormous amounts of hot gas, heated to tens of millions of degrees by gravitational compression. This gas is actually more massive than all the stars in the cluster's galaxies combined. When two clusters collide, their gas clouds smash into each other at speeds of several thousand miles per second. The collision is not gentle. The gas heats up even further as it is compressed. It slows down dramatically due to friction, like two streams of smoke colliding and merging. The gas gets stuck in the middle of the collision, forming a single cloud between the two clusters. The individual galaxies, being much more compact than the gas, pass through each other without much interaction. They continue traveling on their original trajectories, separating from the gas that has piled up in the center. Now here is where dark matter becomes crucial. If the dark matter in each cluster behaved like gas, it would also pile up in the middle. But if dark matter is non-interacting, it would pass right through like the galaxies do. When astronomers used gravitational lensing to map where the mass was located, they found that most of the mass had kept moving. It had passed right through the collision without slowing down. The gas was in the middle, where it had gotten stuck, but the mass was on the outsides, where the clusters had continued traveling. The lensing maps show two massive blobs separated by a region where the X-ray emitting gas is located. The mass is clearly not where the visible matter is. It is where the dark matter would be if dark matter were passing through the collision without interacting. This is exactly what you would expect if most of the mass were dark matter. Unlike gas, dark matter does not interact with itself through friction. It cannot collide and stick together. Two clouds of dark matter can pass right through each other like ghosts walking through walls. Each particle of dark matter ignores every other particle of dark matter, interacting only through gravity. The bullet cluster is considered some of the strongest direct evidence for dark matter's existence. It shows that the mass in galaxy clusters is not the same as the visible matter. The visible matter The gas got stuck in the collision. The invisible matter, the dark matter, passed right through. They separated, and we could see them separate, which proved they were two different things. Some scientists had proposed alternative explanations for the rotation curve problem, suggesting that maybe our understanding of gravity was wrong, rather than that invisible matter existed. The bullet cluster made these alternatives much harder to defend. In the bullet cluster, the mass is clearly separated from the visible matter. If gravity was simply different than we thought, the extra gravitational pull should still be centered on where the visible matter is. But it is not. The extra gravity is somewhere else entirely. It is where the dark matter is. So what is dark matter made of? This is the question that has consumed physicists for decades. We know dark matter exists. We know roughly how much of it there is. We know where it is located and how it behaves. But we still do not know what it actually is. Let me first tell you what dark matter is not. It is not ordinary matter that happens to be dark. When astronomers first proposed dark matter, some suggested it might just be normal matter in forms we could not see. Dead stars, for example, or planets floating between the stars, or clouds of cold gas and dust. These are sometimes called MACOs, which stands for Massive Astrophysical Compact Halo Objects. The idea had some appeal. After all, we know that space contains many objects that do not emit their own light. Failed stars called brown dwarfs glow only dimly in the infrared. White dwarfs, the remnants of stars like our Sun, are small and faint. Neutron stars are even smaller and harder to detect. Black holes emit no light at all. Could the dark matter in galaxy halos simply be vast numbers of these invisible but otherwise ordinary objects? Scientists spent years searching for MACOs using a technique called gravitational microlensing. The idea is that if a compact dark object, like a dead star, passes between us and a distant star, its gravity will briefly magnify the light from the background star. By monitoring millions of stars and looking for these brief brightenings, astronomers could search for invisible objects in our galaxy's halo. The most extensive searches were conducted in the 1990s and 2000s by projects with names like MACO, Eros, and Ogle. These collaborations monitored tens of millions of stars in the Magellanic Clouds and toward the center of the Milky Way, watching for the characteristic brightening that would indicate a compact object passing in front. They found some. There are definitely brown dwarfs and other dim objects out there, but there are nowhere near enough to account for all the missing mass. The microlensing surveys showed that MACOs could make up at most about 20% of the dark matter halo, and probably much less than that. Ordinary matter in dark forms might make up a few percent of dark matter at most. The vast majority must be something else. This conclusion is reinforced by another line of evidence. The Big Bang produced elements in specific proportions. The amount of hydrogen, helium, and lithium created in the first few minutes after the Big Bang depended on the total density of ordinary matter, the stuff made of protons and neutrons. By measuring the abundances of these elements today, cosmologists can calculate how much ordinary matter the universe contains. The answer is about 5% of the total energy density of the universe. This matches the amount of ordinary matter we see in stars, gas, and planets. There is no room for a hidden reservoir of ordinary matter that could account for dark matter. Whatever dark matter is, it cannot be made of protons and neutrons. It must be something new. Dark matter is also not made of neutrinos, at least not entirely. Neutrinos are ghostly particles produced in nuclear reactions, including the fusion reactions in the Sun. They barely interact with ordinary matter at all. The Sun produces about 200 trillion neutrinos every second, and many of them reach Earth, yet we never notice them. They seemed like good dark matter candidates, but neutrinos move too fast. They zip through space at nearly the speed of light. This would have prevented them from clumping together in the early universe. If dark matter were made of neutrinos, the cosmic structure would look different than what we observe. The galaxies would be larger and more diffuse. The voids would be smaller. The details do not match. Physicists describe this by distinguishing between hot dark matter and cold dark matter. Hot dark matter consists of fast-moving particles like neutrinos. Cold dark matter consists of slower-moving particles that can clump together more easily. All of our observations suggest that most dark matter is cold. So what could cold dark matter be? The leading candidates are particles that have been theorized but never detected. They exist in the equations of theoretical physics, but not yet in our laboratories. If they are real, they must interact very rarely with ordinary matter, which is why we have not found them yet. They must be stable, lasting for billions of years without decaying. And they must have formed in the right quantities in the early universe. The most popular candidates for many years were called WIMPs, which stands for Weakly Interacting Massive Particles. These would be particles that interact through the weak nuclear force, one of the four fundamental forces of nature. The weak force is responsible for certain kinds of radioactive decay. It is called weak because it operates only over very short distances and produces relatively rare interactions. WIMPs are appealing because several extensions to the standard model of particle physics naturally predict particles with the right properties. In particular, a theory called supersymmetry suggests that every known particle has a heavier partner particle, and the lightest of these partner particles would be stable and would make an excellent dark matter candidate. But WIMPs have a problem. Despite decades of searching, we have never found one. The search for WIMPs began in earnest in the 1980s. Early experiments were modest by today's standards, using detectors weighing just a few kilograms. The idea was simple. Wait for a dark matter particle to collide with an atomic nucleus in the detector and measure the tiny amount of energy deposited. Think about how rare such a collision would be. The Milky Way's dark matter halo contains an enormous number of particles, all in constant motion. A typical dark matter particle could travel straight through the entire Earth, entering one side and exiting the other, without ever touching a single atom. The chances of one stopping in a detector weighing just a few kilograms are extraordinarily small. Early estimates suggested that a kilogram of detector material might see one WIMP collision per day, or maybe per month. This seemed like a challenging but achievable goal. Scientists built detectors, shielded them from background radiation, and waited. The first major result came in 1986, when a collaboration in France reported limits on WIMP interactions. They had not detected anything, but they could say that WIMPs were not interacting more often than a certain rate. This was the beginning of a long tradition of null results. Through the 1990s, experiments grew larger and more sophisticated. The CDMS collaboration in the United States used germanium crystals cooled to near absolute zero. The Dharma collaboration in Italy used sodium iodide crystals and claimed to see a signal, though other experiments could not confirm it. The Edelweiss experiment in France and the Zeppelin experiments in the United Kingdom joined the hunt. Each experiment set more stringent limits. If WIMPs existed, they had to be interacting less often than the previous generation of experiments could detect. The goalposts kept moving, always just out of reach. By 2010, the sensitivity of direct detection experiments had improved by a factor of 1,000,000 compared to the first experiments. The Lux experiment, using 300 kilograms of liquid xenon, achieved sensitivities that would have seemed like science fiction just 2 decades earlier. Still, no WIMPs. The 2020s brought even more powerful experiments. LZ with 10 tons of xenon and Xenont with similar capabilities pushed the limits further still. The experiments can now detect interactions 1,000,000,000 times rarer than what early experiments were sensitive to. And still nothing. Experiments around the world have been hunting for WIMPs since the 1980s. The basic approach is straightforward. You take a large detector filled with some target material, put it deep underground to shield it from cosmic rays and other interference, and wait for a dark matter particle to bump into one of your atoms. If dark matter interacts through the weak force, occasional collisions should happen, producing tiny flashes of light or heat that sensitive instruments can detect. The experiments have gotten more and more sensitive over the years. The current generation of detectors can detect incredibly faint signals, far fainter than anyone thought possible a few decades ago. They have ruled out large swaths of the parameter space where WIMPs could exist. If WIMPs are real, they must be either lighter or more weakly interacting than most theories predicted. This does not mean WIMPs are impossible. There is still room in the equations for particles we have not detected yet. But the failure to find them after so many years of searching has led many physicists to consider alternative candidates. One increasingly popular alternative is the axion. Axions are hypothetical particles that were originally proposed to solve a different problem in physics entirely. A problem having to do with why the strong nuclear force does not violate certain symmetries that it theoretically could violate. The solution was a new particle, very light and very weakly interacting, that would naturally have the properties needed for dark matter. The axion has a strange history. It was invented in 1977 by Roberto Pecci and Helen Quinn as a solution to something called the strong CP problem. This is a technical issue in quantum chromodynamics, the theory of the strong nuclear force. The equations of the theory allow for a kind of asymmetry that would make neutrons have electric dipole moments. But experiments show that neutrons do not have measurable electric dipole moments. Why not? Pecci and Quinn proposed that a new symmetry of nature would automatically set the relevant parameter to 0. But new symmetries in physics often come with new particles. Frank Wilczek and Steven Weinberg, working independently, showed that the Pecci-Quinn symmetry implied the existence of a new, very light particle. Wilczek named it the axion, after a brand of laundry detergent, because it cleaned up a messy problem in physics. If axions are the dark matter, they would be incredibly light, perhaps 1,000,000,000,000 times lighter than an electron. They would be so light that they would behave more like a wave than a collection of particles. Enormous numbers of them would be packed into every cubic inch of space, vibrating in unison like a cosmic background hum. The axion is a strange kind of particle. It would not behave like the particles we are familiar with. It would not zip around like a bullet. Instead, axions would form a coherent field that oscillates at a specific frequency determined by their mass. This oscillating field would pervade all of space, invisible and intangible but present everywhere. Detecting such a field requires completely different techniques than detecting WIMPs. Several experiments are now searching for axions by looking for their interaction with strong magnetic fields. The idea is that an axion passing through a magnet might occasionally convert into a photon, which could then be detected. These experiments have not found axions yet either, but they are still in relatively early stages compared to the WIMP searches. There are other candidates too. Primordial black holes, formed in the chaotic conditions of the early universe, could potentially make up some or all of dark matter. Sterile neutrinos, a hypothetical, heavier cousin of ordinary neutrinos, are another possibility. Particles from extra dimensions predicted by string theory have been proposed. The list goes on. The honest truth is that we do not know what dark matter is. After nearly a century of knowing it exists, we still cannot identify the particle or particles that compose it. This is humbling. It is also exciting. There is a major discovery waiting to be made, a discovery that will fundamentally change our understanding of the universe. Let me take you on a tour of some of the experiments currently searching for dark matter. These are remarkable feats of engineering, pushing the boundaries of what is possible in terms of sensitivity and precision. One of the most sensitive dark matter detectors in the world is located nearly a mile underground in South Dakota, in a former gold mine called the Homestake Mine. The experiment is called Lux Zeppelin, or LZ for short. It consists of a massive tank filled with 10 metric tons of ultra-pure liquid xenon. The Homestake Mine has a special place in the history of physics. In the 1960s, it was home to the first solar neutrino experiment. Conducted by Raymond Davis Jr., Davis placed a tank of cleaning fluid deep in the mine and waited for neutrinos from the sun to convert chlorine atoms into argon atoms. His experiment detected fewer neutrinos than expected, a puzzle that eventually led to the discovery that neutrinos have mass and can change from one type to another. Davis won the Nobel Prize in 2002 for this work. Today, the same mine hosts one of the most ambitious dark matter searches ever attempted. The cavern where the LZ detector sits was carved out of the rock at a depth of 4,850 feet. At this depth, the rock above blocks nearly all of the cosmic rays that bombard the surface. Getting 10 tons of liquid xenon a mile underground is no small feat. The xenon had to be purified to unprecedented levels of cleanliness. Any trace of radioactivity in the xenon would produce signals that could mimic dark matter. The purification process involves passing the xenon through filters and distillation columns, removing radon and krypton and other contaminants down to levels of parts per quadrillion. The detector itself is an engineering marvel. At its heart is a cylindrical tank about 5 feet tall and 5 feet in diameter, filled with liquid xenon at -148 degrees Fahrenheit. Surrounding this central tank is a layer of additional xenon that acts as a shield, detecting any particles that penetrate from outside. Beyond that are layers of water and other shielding materials. When a particle interacts with a xenon atom in the detector, two things happen. First, the xenon produces a flash of ultraviolet light. Second, electrons are knocked free from the xenon atoms. An electric field pulls these electrons upward through the liquid and into a thin layer of gaseous xenon at the top. When the electrons enter the gas, they produce a second flash of light. By detecting both flashes and measuring the time between them, scientists can determine where in the detector the interaction occurred and how much energy was deposited. Different types of particles leave different signatures. A dark matter particle would produce a distinctive pattern that in principle could be distinguished from the background. Why liquid xenon? Because xenon is dense and produces characteristic signals when a particle interacts with it. If a dark matter particle were to bump into a xenon nucleus, the xenon would produce both light and electrical charge. By detecting both signals, scientists can distinguish genuine dark matter interactions from background noise caused by radioactivity or cosmic rays. Why underground? Because the surface of the Earth is constantly bombarded by particles from space. Cosmic rays produced by exploding stars and other energetic events shower down on us all the time. These would completely overwhelm any dark matter signal if the detector were at the surface. By placing the detector deep underground, the rock above acts as a shield, blocking the cosmic rays while allowing dark matter to pass through. Dark matter interacts so weakly that even miles of rock cannot stop it. The level of purity required for these experiments is extraordinary. Every component of the detector must be screened for radioactive contamination. Even trace amounts of natural radioactivity, from elements like uranium or thorium, can produce signals that mimic dark matter. The xenon itself must be purified to remove any radioactive isotopes. The air in the facility is filtered. The water is purified. Everything that goes underground is carefully selected to be as radio pure as possible. Despite all these precautions, the experiments have not detected dark matter. What they have done is set increasingly stringent limits on what dark matter could be. Each null result rules out more possibilities, narrowing the range of properties that dark matter particles could have. This is progress, even if it does not feel like a discovery. Across the Atlantic, in the Gran Sasso Mountain in Italy, similar experiments are underway. The Xenon collaboration operates a detector called Xenont, which also uses liquid xenon and has comparable sensitivity to LZ. In China, the Pandax experiment pursues the same goal with similar technology. These experiments are in a friendly competition, each trying to be the first to detect dark matter directly. Other experiments use different approaches. The CDMS experiment, located in a mine in Minnesota, uses germanium and silicon crystals cooled to temperatures colder than outer space. At these frigid temperatures, a dark matter particle colliding with an atom would produce vibrations, tiny phonons, that can be detected with exquisite sensitivity. The PICO experiment uses superheated liquid, which would form bubbles if a dark matter particle collided with a nucleus. Each approach has advantages and disadvantages, and running multiple experiments increases the chances that at least one will succeed. Then there are the Axion experiments. ADMX, the Axion Dark Matter Experiment, operates at the University of Washington in Seattle. It uses a powerful magnet and a precisely tuned cavity to search for axions converting into photons. The cavity must be tuned to exactly the right frequency to match the mass of the axion, and since we do not know what that mass is, the experiment slowly scans through different frequencies, listening for a signal. There are also experiments that search for dark matter indirectly by looking for its annihilation products. If dark matter particles are their own antiparticles, they might occasionally annihilate when they meet each other, producing ordinary particles like gamma rays or neutrinos or charged particles. The idea is straightforward. Dark matter particles are constantly moving through the galaxy, crisscrossing in every direction. Most encounters between dark matter particles result in nothing at all, both particles continuing on their way unaffected. But if they have even a tiny probability of annihilating when they meet, then, in regions where the dark matter density is highest, we might be able to detect the products of these rare annihilation events. Where would we look? The center of the Milky Way is a good place to start. The dark matter density should be highest there, where the gravitational potential is deepest. Other promising targets include the centers of dwarf galaxies, galaxy clusters, and even the Sun, where dark matter particles might accumulate over billions of years. Space-based telescopes like the Fermi Gamma Ray Space Telescope scan the sky for excess gamma rays that might come from dark matter annihilation. Fermi has been operating since 2008, building up the most detailed all-sky map of gamma ray sources ever created. It has detected thousands of gamma ray sources, including pulsars, black holes, supernova remnants, and active galaxies. Some researchers have claimed to see an excess of gamma rays from the galactic center that could be dark matter annihilation. But the galactic center is a complicated place, full of ordinary astrophysical sources that also produce gamma rays. Distinguishing a dark matter signal from this background is extremely difficult. Most astronomers remain skeptical that the excess is really dark matter. The Ice Cube Neutrino Observatory, a massive detector buried in the ice at the South Pole, searches for neutrinos that might be produced when dark matter particles accumulate and annihilate in the cores of the Sun or Earth. IceCube consists of over 5,000 optical sensors frozen into a cubic kilometer of Antarctic ice. When a high-energy neutrino interacts with ice, it produces a brief flash of light that these sensors can detect. So far, none of these indirect searches have produced definitive evidence of dark matter either. There have been tantalizing hints and anomalies over the years, signals that seemed like they might be dark matter but eventually turned out to have other explanations. The search continues. At this point, you might be wondering if we have gotten something fundamentally wrong. If we have been looking for dark matter for so long without finding it, maybe dark matter does not exist at all. Maybe the problem is not invisible matter, but our understanding of gravity. This idea has a long history. In 1983, an Israeli physicist named Mordechai Milgrom proposed an alternative to dark matter called MOND, which stands for Modified Newtonian Dynamics. Milgrom suggested that Newton's law of gravity might not be quite right at very low accelerations. In the outer regions of galaxies, where stars experience very weak gravitational forces, gravity might be slightly stronger than Newton's equations predict. The idea came from a simple observation. The acceleration at which galactic rotation curves start to deviate from Newtonian predictions is always about the same, roughly 1/10,000,000th of the acceleration we feel on Earth's surface. This seems like too much of a coincidence. Why should dark matter always arrange itself so that the deviation happens at this particular acceleration? Milgrom proposed that there is no dark matter. Instead, gravity itself changes its behavior at very low accelerations. In our everyday experience, with accelerations much larger than this threshold, gravity works exactly as Newton described. But in the outer reaches of galaxies, where accelerations are extremely weak, gravity is stronger than Newton would predict. MOND can explain galaxy rotation curves without invoking dark matter. By tweaking the law of gravity, Milgrom could match the observed rotation speeds of stars in the outer regions of galaxies. No invisible matter required. Just a small modification to physics. The MOND formula is remarkably simple. It introduces just one new parameter, the acceleration scale at which the modification kicks in. With this single number, MOND can predict the rotation curves of hundreds of galaxies. In many cases, it does so more accurately than dark matter models that have multiple adjustable parameters. This predictive power is impressive. Before observing a galaxy, you can use MOND to calculate what its rotation curve should look like based only on the distribution of visible matter. When astronomers do this, the predictions often match observations closely. This is what proponents of MOND call the mass discrepancy acceleration relation, and it remains one of the most intriguing empirical regularities in astronomy. There is something elegant about this idea. It solves the problem with a change to known physics rather than the introduction of an entirely new form of matter. And for many years, MOND had some notable successes. It correctly predicted the rotation curves of many galaxies, sometimes more accurately than dark matter models. But MOND has problems too. It struggles to explain galaxy clusters, where the missing mass is even more pronounced than in individual galaxies. It cannot easily account for the cosmic microwave background, the pattern of light left over from the early universe, which matches dark matter predictions remarkably well. And the bullet cluster is particularly challenging for MOND, because the missing mass is clearly separated from the visible matter, which should not happen if gravity is simply modified. In recent years, physicists have tried to develop more sophisticated versions of modified gravity that can address these issues. Theories like TVES, developed by Jacob Bekenstein, attempt to create a relativistic version of MOND that is compatible with Einstein's theory of gravity. These theories are mathematically complex and have had mixed success in explaining observations. Most cosmologists today believe that dark matter is more likely than modified gravity. The evidence from multiple independent sources, galaxy rotation curves, galaxy clusters, gravitational lensing, the cosmic microwave background, the formation of large-scale structure, all points toward the existence of invisible matter. While modified gravity can explain some of these observations individually, dark matter provides a unified explanation for all of them. But the debate is not entirely settled. As long as we have not directly detected dark matter particles, there will be scientists who explore alternative explanations. This is how science should work. We follow the evidence wherever it leads, and we remain open to the possibility that our current understanding is incomplete. Let me now address a common point of confusion. Dark matter and dark energy are not the same thing. They sound similar, and they are both invisible, but they are completely different phenomena. Dark matter is matter. It has mass. It exerts gravitational attraction. It pulls things together. Without dark matter, galaxies would fly apart and the cosmic web would not exist. Dark energy is something else entirely. It is a property of space itself, a kind of anti-gravity that causes the expansion of the universe to accelerate. While dark matter pulls things together, dark energy pushes them apart. While dark matter helps form structures, dark energy is slowly tearing those structures apart on the largest scales. To understand dark energy, we need to think about the history of the universe's expansion. After the Big Bang, the universe began expanding. All the galaxies started moving away from each other. For most of cosmic history, this expansion was slowing down, as you would expect. The gravitational attraction of all the matter in the universe was acting as a brake, pulling everything back together and gradually decelerating the expansion. Scientists expected that the expansion would continue to slow. Eventually, gravity might even halt the expansion entirely, possibly leading to a big crunch where the universe collapsed back to a single point. Or the expansion might slow to a crawl but never quite stop, with the universe gradually approaching a final static state. What nobody expected was for the expansion to speed up. Dark energy was discovered in 1998, when two teams of astronomers were measuring distant supernovas to understand the expansion history of the universe. Supernovas are exploding stars, and a particular type called Type Ia supernovas all have about the same intrinsic brightness. This makes them useful as distance indicators. By measuring how bright a distant supernova appears, astronomers can calculate how far away it is. The two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were measuring supernovas billions of light-years away. By comparing the distances to these supernovas with their redshifts, which tell us how much the universe has expanded since the light was emitted, they could reconstruct the expansion history of the cosmos. Both teams expected to find that the expansion was slowing down. Instead, they found the opposite. Distant supernovas were fainter than expected, which meant they were farther away than expected. The universe was not decelerating. It was accelerating. Something was pushing the universe apart, faster and faster. This discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. It was one of the most shocking findings in the history of cosmology. We call this mysterious force dark energy, because, like dark matter, we do not understand what it is. It makes up about 68% of the total energy content of the universe. Combined with dark matter at 27%, this means that ordinary matter, the stuff that makes up stars and planets and people, accounts for only about 5% of everything. This is one of the most remarkable discoveries in the history of science. We used to think we understood what the universe was made of. Now we know that we only understand about 5% of it. The other 95% remains mysterious. Dark matter and dark energy are the two greatest puzzles in modern cosmology. They are connected in the sense that both are invisible and both are necessary to explain our observations. But they are fundamentally different in nature and require different explanations. So where does this leave us? What is the current state of dark matter research, and what might the future hold? The search for dark matter is entering a new phase. After decades of null results from direct detection experiments, scientists are not giving up. They are building bigger and more sensitive detectors. The next generation of experiments, with names like Darwin and XLZD, will be even more capable than the current ones. They will probe deeper into the parameter space where dark matter might be hiding. Darwin is a proposed experiment that would use 50 tons of liquid xenon, 5 times more than LZ. At this scale, the experiment would be sensitive enough to detect even the rarest WIMP interactions predicted by theory. It would also start to encounter an unavoidable background from neutrinos, which will eventually set a fundamental limit on direct detection experiments. This is sometimes called the neutrino flaw, the point at which neutrino signals become indistinguishable from potential dark matter signals. XLZD, a collaboration between the LZ and Xenon teams, is planning an even larger experiment. The goal is to push sensitivity to the very edge of what is physically possible with this technique. If WIMPs exist and have properties anywhere close to what theory predicts, these experiments should find them. If they do not find anything, it will be strong evidence that we need to look elsewhere. There is also renewed interest in alternative candidates. Axions, once considered exotic, are now mainstream. New experiments designed specifically to detect axions are coming online. Abracadabra, a clever experiment using toroidal magnets, is searching for axions at very low masses. Caspar uses nuclear magnetic resonance techniques to look for the effects of axion-like fields. Haystack and other cavity experiments are scanning through higher axion masses. The diversity of approaches reflects the uncertainty about what dark matter actually is. Since we do not know the mass or interaction strength of dark matter particles, we have to search across a wide range of possibilities. Different experiments are optimized for different regions of parameter space. Together, they cover an enormous range of potential dark matter properties. Primordial black holes are being reconsidered as serious contenders. Theorists are proposing new particles and new models that could explain dark matter in unexpected ways. Particle accelerators like the Large Hadron Collider continue to search for evidence of new physics that might illuminate the dark matter mystery. If dark matter is connected to the supersymmetric particles that the collider might produce, we could learn about its properties by studying the debris of high-energy collisions. Astronomical observations are also improving. New telescopes, both on the ground and in space, are mapping the distribution of dark matter with unprecedented precision. The Vera C. Rubin Observatory, named after the astronomer who discovered galaxy rotation curves, is beginning operations in Chile. It will survey the entire visible sky repeatedly, tracking the positions and shapes of billions of galaxies to map dark matter through gravitational lensing. The Euclid Space Telescope, launched by the European Space Agency in 2023, is dedicated to studying dark energy and dark matter. It will create the largest and most accurate three-dimensional map of the universe ever made, measuring how dark matter is distributed across billions of light years. These observations will not tell us what dark matter is made of. For that, we need direct detection or production in a laboratory. But they will tell us how dark matter behaves, how it clusters, how it interacts with itself, if it interacts at all. And those clues might help us figure out what we are looking for. Let me step back and consider the bigger picture. Why does dark matter matter? From a practical standpoint, understanding dark matter might seem irrelevant. It does not affect your daily life in any obvious way. It does not power your car, or grow your food, or cure diseases. You cannot see it, or touch it, or use it for anything. But from a deeper perspective, dark matter is one of the most important mysteries we face. It is a reminder that the universe is far stranger than we imagined. It challenges our assumptions about what matter is and how the universe works. For centuries, humans have been learning that we are not as special as we thought. The Earth is not the center of the universe. The Sun is just one of billions of stars in our galaxy. Our galaxy is just one of billions in the observable universe. And now we know that everything we can see, every star and planet and person, makes up only a tiny fraction of what actually exists. Dark matter humbles us. It tells us that there are aspects of reality we do not understand and may never fully understand. It reminds us that nature does not owe us an easy answer. But dark matter also inspires us. The fact that we discovered something invisible, something that refuses to interact with our instruments, is a testament to human ingenuity. We figured out that something was missing by carefully observing how things move. We mapped its distribution by measuring how it bends light. We have spent decades designing ever more sensitive experiments to detect its particles. This is science at its best, persistent, creative, driven by curiosity. And there is something beautiful about dark matter too. It is the hidden structure beneath the visible universe. Every galaxy floats in a sea of dark matter. Every star formed within a dark matter cocoon. The visible universe is just the foam on an invisible ocean. Let me tell you about some of the most recent developments in dark matter research, to give you a sense of where the field stands right now. In 2023, the LZ experiment released its first results. After months of data collection, they found no evidence of dark matter particles. This was disappointing, but not surprising. What was impressive was how sensitive the detector had become. LZ set new limits on the cross-section of WIMP interactions, pushing the bounds tighter than any previous experiment. Around the same time, the Xenon collaboration reported similar null results from Xenont. Both experiments are continuing to take data, and their sensitivity will improve as they accumulate more statistics. The absence of a signal is itself informative. It tells us that if WIMPs exist, they must interact even more weakly than theorists originally expected. On the axion front, ADMX has continued its slow scan through possible axion masses. They have ruled out axions in certain mass ranges but have not found a signal yet. New experiments with different designs are being planned to search at higher and lower masses. There have also been some intriguing anomalies. The Dharma Libra experiment in Italy has been claiming to detect an annual modulation in their signal for over 2 decades. The idea is that as the Earth orbits the Sun and the Sun orbits the galactic center, we move through the dark matter halo at different speeds throughout the year. This should cause a tiny seasonal variation in dark matter collision rates. Dharma Libra sees this annual modulation. But no other experiment has been able to replicate their result, despite using similar and even the same detector materials. Most physicists are skeptical that Dharma is seeing dark matter. The signal is more likely due to some unaccounted for systematic effect. But the controversy continues. There have also been hints from indirect detection. The Fermi Space Telescope has observed an excess of gamma rays coming from the center of our galaxy. Some researchers interpreted this as evidence of dark matter annihilation. Others pointed out that the excess could be explained by a population of millisecond pulsars, rapidly spinning neutron stars that emit gamma rays. The debate is ongoing, with new analyses and new data continuing to refine our understanding. What is clear is that dark matter research is not stagnating. The field is active and advancing on multiple fronts. The experiments are getting more powerful. The theoretical ideas are becoming more sophisticated. The astronomical observations are becoming more precise. Even if we have not found dark matter yet, we are learning more about the universe every year. Let me share with you some of the more speculative ideas about dark matter that scientists are exploring. These are not mainstream theories, but they show the range of thinking in the field. One idea is that dark matter might have its own rich physics. Just as ordinary matter comes in many forms, protons and neutrons, and electrons and photons, dark matter might also come in multiple types of particles with their own interactions. There might be dark photons, dark versions of the force carriers that ordinary matter uses. There might be dark atoms, composed of dark protons and dark electrons bound together by dark electromagnetism. If this dark sector exists, it would be a hidden world running parallel to our own. Dark matter might form dark planets, dark stars, even dark galaxies. These structures would be completely invisible to us, interacting with our universe only through gravity. Some physicists have even speculated about dark life. If dark matter can form complex structures, could those structures develop the ability to reproduce and evolve? This is almost certainly science fiction rather than science, but it illustrates how little we know about what dark matter might be capable of. The idea of a dark sector is not entirely without observational constraints. If dark matter had strong self-interactions, it would behave differently in galaxy collisions than if it were completely non-interacting. The halos of galaxies might have different shapes. There might be dark matter substructures that leave detectable gravitational imprints, Observations of galaxy clusters and galaxy shapes have placed limits on how strongly dark matter can interact with itself. These limits are still fairly weak, leaving room for a dark sector with modest interactions. But the strongest self-interactions, the ones that would allow for complex dark structures, seem to be ruled out by the data. This idea is hard to test, but it is not impossible. If dark matter interacts with itself, it would behave differently in galaxy collisions than if it were completely non-interacting. The halos of galaxies might have different shapes. There might be dark matter substructures that leave detectable gravitational imprints. Another speculative idea is that dark matter might be connected to extra dimensions. String theory, a theoretical framework that attempts to unify all the forces of nature, predicts that the universe might have more dimensions than the three of space and one of time that we experience. Particles might exist in these extra dimensions, and gravity might leak between dimensions in ways that could explain dark matter. If extra dimensions are real, dark matter might not be matter at all in the conventional sense. It might be the gravitational influence of matter in another dimension, matter that we cannot access but whose gravity reaches into our own dimension. These ideas are speculative, and there is no direct evidence for them. But they show that scientists are willing to think beyond the conventional framework when conventional ideas fail to produce answers. The universe has surprised us before. It might surprise us again. As we approach the end of this journey, I want to reflect on what dark matter tells us about the nature of scientific discovery. Science is often portrayed as a series of eureka moments, sudden flashes of insight that reveal the secrets of the universe. In reality, most science is much slower and more incremental. Dark matter was not discovered in a single moment. It was pieced together over decades through the painstaking work of hundreds of scientists building on each other's observations. The story is also one of frustration. Zwicky proposed dark matter in 1933. Nearly a century later, we still do not know what it is. Generations of physicists have worked on this problem without solving it. Experiments have been built, run, and retired without detecting a signal. Theories have been proposed, tested, and discarded. This might seem like failure, but it is not. Each null result teaches us something. Each unsuccessful experiment narrows the possibilities. Science advances by ruling things out, as well as by finding things. We know more about dark matter today than we did 50 years ago, even though we have not found it yet. There is also a lesson here about the limits of human knowledge. We like to think that we can understand everything, that the universe is ultimately comprehensible. Dark matter challenges this assumption. It has resisted our best efforts for nearly a century. It may continue to resist for decades more. There is no guarantee that we will ever identify the particles that compose it. But this uncertainty is not a reason for despair. It is a reason for wonder. The universe is vast and strange and full of mysteries. Dark matter is one of them. The fact that we know it exists, even if we do not know what it is, shows how far we have come. The fact that we are still searching shows how much there is left to discover. Let me leave you with a thought about perspective. Right now, as you listen to this, you are embedded in a halo of dark matter. The Milky Way galaxy, our home, is surrounded by a cloud of invisible matter that extends for hundreds of thousands of light years. You are swimming in an ocean you cannot see. Dark matter particles drift through you constantly, billions per second, never stopping, never slowing, continuing on journeys that have lasted billions of years. You are, in a very real sense, shaped by invisible matter. Not directly, of course. Your atoms are ordinary matter, protons and neutrons and electrons, the stuff we understand. But the gravity that shapes your environment, the force that holds galaxies together and allows stars to form and planets to coalesce, that gravity is dominated by dark matter. Without dark matter, the gas that became the sun would never have collapsed. Without dark matter, the rocky material that became the Earth would never have accumulated. Without dark matter, the complex chemistry that led to life would never have occurred. You owe your existence to something you cannot see and may never fully understand. This is humbling. It is also beautiful. The visible universe, all the stars and planets and nebulae that we photograph and admire, is just a thin coating on an invisible foundation. We live in the luminous fringe of a mostly dark cosmos. Most of reality is hidden from us, and yet we discovered it. Through careful observation and clever reasoning, we figured out that the visible universe is not all there is. We mapped the invisible. We measured what we cannot see. This is one of humanity's greatest achievements. The story of dark matter is not over. The mystery remains unsolved. But the fact that we know the mystery exists is itself a triumph. It means the universe is larger and stranger than we ever imagined. It means there are discoveries still to be made, puzzles still to be solved, wonders still to be found. Somewhere out there, in a laboratory underground, or a telescope pointed at the sky, or a theoretical calculation scribbled on a whiteboard, someone is working on this problem right now. They are chipping away at the mystery, trying to find the piece that unlocks everything. And someday, perhaps in your lifetime, they might succeed. When that day comes, when we finally understand what dark matter is, it will be one of the greatest discoveries in the history of science. It will rewrite our understanding of physics and cosmology. It will answer questions that have haunted us for a century. But even if that day never comes, even if dark matter remains forever mysterious, the search itself has value. It has pushed the boundaries of technology and expanded the frontiers of knowledge. It has shown us that the universe is more complex than we imagined. And it has reminded us that there are things in this cosmos beyond our understanding, secrets waiting to be discovered, mysteries that may take centuries to solve. Dark matter is out there, invisible and patient, shaping the universe in ways we can measure but not see. It binds galaxies that would otherwise fly apart. It guides the formation of stars. It is woven into the fabric of the cosmos, a hidden thread in the tapestry of reality. The dark matter around you is ancient. Most of it was created in the first moments after the Big Bang, nearly 14 billion years ago. It has been drifting through the universe ever since, clumping together under its own gravity, forming the halos that would later attract ordinary matter and give birth to galaxies. These particles have traveled enormous distances. They have orbited the galaxy countless times. They were present when the first stars ignited, when the Earth formed, when life emerged from the primordial oceans. They carry no record of what they have witnessed, no memory of the cosmic drama that unfolded around them. They simply drift, indifferent and eternal. The typical dark matter particle in our galaxy moves at about 220 miles per second relative to the galactic center. That is fast by human standards, but slow compared to light. These particles orbit the galaxy in roughly 250 million years, the same period it takes our sun to complete one galactic orbit. But while our sun follows a nearly circular path through the disk, dark matter particles have more random orbits, swooping in toward the center and back out again in elongated ellipses. There is something both humbling and wondrous about this. We are surrounded by witnesses to cosmic history, travelers who have been everywhere and seen everything, and we cannot even detect their presence. We know they are there only because of the subtle pull they exert on the things we can see. We live in a universe of invisible wonders. Dark matter is one of them. There is something else worth considering about dark matter, something that speaks to the relationship between observation and understanding. For most of history, humans believed that knowledge came from direct experience. You know something is real because you can see it, touch it, hear it. The world was what your senses told you it was. This worked well enough for everyday life. If you could not perceive something, it was irrelevant. But science has gradually revealed that our senses are limited. We cannot see radio waves or X-rays without special instruments. We cannot hear sounds that are too high or too low in frequency. We cannot feel the magnetic fields that surround us. And we certainly cannot perceive dark matter. Yet dark matter is real. It affects the universe in measurable ways. It bends light and shapes galaxies and determines the structure of the cosmos. Its reality does not depend on our ability to see it. It exists whether we perceive it or not. This is a profound lesson about the nature of reality. The universe is not limited to what we can experience directly. There are aspects of existence that are forever beyond our senses, accessible only through inference and calculation. Dark matter is a reminder that reality is larger than perception. It also raises questions about what else might be out there. If something as significant as dark matter could go undetected for so long, what other hidden aspects of reality might we be missing? What other invisible forces might be shaping the cosmos in ways we have not yet discovered? These questions do not have easy answers. They might not have any answers at all, but they keep scientists awake at night, pondering the limits of knowledge and the vastness of the unknown. The instruments we use to study dark matter are marvels of precision engineering. Consider what it takes to detect a particle that almost never interacts with anything. In a typical dark matter experiment, you are waiting for a single particle to collide with a single nucleus in a detector containing trillions of atoms. The collision, if it happens, will deposit a tiny amount of energy, perhaps a few billionths of a joule. This is less energy than a mosquito uses in a single wing beat. And you need to detect this infinitesimal signal amid a constant background of noise from cosmic rays, radioactivity, vibrations, and thermal fluctuations. To achieve this, scientists have developed technologies that border on the magical photomultiplier tubes, can detect individual photons, the smallest possible unit of light. Cryogenic detectors, cooled to within a fraction of a degree of absolute zero, can sense the vibration of a single atom. Ultra-pure materials are manufactured with contamination levels measured in parts per trillion. The engineering challenges are immense. The LZ detector, for example, contains over 250 photomultiplier tubes, each one carefully tested and selected for minimal radioactivity. The xenon itself has been purified through multiple cycles of distillation and circulation. The detector is suspended in a bath of even more xenon, which acts as an active veto to reject events from the outer edges. Every aspect of the design is optimized for one purpose: to catch a dark matter particle in the act. And despite all this effort, the detectors sit silent. Day after day, year after year, nothing happens. Or rather, things happen, but they are all background events. Cosmic ray muons slip through the rock. Radioactive decays occur in the materials of the detector. Neutrons from the rock walls scatter off nuclei. Each event must be carefully analyzed and rejected. leaving only a vanishingly small number of candidates that might, conceivably, be dark matter. So far, none of them have been. The psychology of searching for something that refuses to be found is interesting. You might think that decades of null results would be demoralizing. And for some researchers, it probably is. But for many, the challenge is invigorating. There is something deeply human about the hunt for dark matter. It is a quest in the classical sense. A group of dedicated individuals pursuing a goal that has eluded everyone who came before them. They know the search might take decades more. They know they might not be the ones to succeed, but they keep going anyway, driven by curiosity and the hope that the next experiment, the next observation, the next theoretical insight might be the one that cracks the case. The dark matter community has developed a culture of careful skepticism. When someone claims to detect a signal, the reaction is not celebration, but scrutiny. Every result is questioned. Every systematic error investigated. Every alternative explanation considered. This is science at its most rigorous. The standard of proof is extraordinarily high because the stakes are so significant. False alarms have happened before. In 2011, the Cogent experiment reported a possible annual modulation signal similar to Dharma's. Excitement flared briefly before other experiments failed to confirm the result. In 2016, a bump in the data at the Large Hadron Collider looked like it might be a new particle related to dark matter. A year later, with more data, the bump disappeared. Each time, the community absorbed the disappointment and moved on. The search continued, the experiments improved, the theories evolved. This resilience is one of the strengths of scientific culture. No single result is trusted until it has been independently confirmed. No claim is accepted without rigorous testing. When dark matter is finally detected, if it is finally detected, the announcement will come after exhaustive verification. It will be scrutinized by dozens of independent groups. It will be tested against every alternative explanation. Only when all other possibilities have been eliminated will the discovery be accepted. That day may be tomorrow. It may be decades from now. It may never come, but the search goes on. Let me tell you about some of the patterns dark matter creates in the universe. These patterns are visible to our telescopes, even though the dark matter itself is not. On the largest scales, dark matter forms the cosmic web we discussed earlier. But within that web, there are finer structures. Dark matter halos are not smooth. They are lumpy and clumpy, filled with subhalos of denser dark matter embedded within the larger halo. Our own Milky Way has many of these subhalos. Some of them contain visible matter, dwarf galaxies that orbit the Milky Way like the Magellanic Clouds. But many subhalos are completely dark, containing only dark matter without any stars or gas. These invisible satellites orbit our galaxy, tugging on the visible matter with their gravity but never revealing themselves through light. We can detect these dark subhalos through their gravitational effects. They distort the shapes of streams of stars that orbit the galaxy. They perturb the motions of stellar associations. They leave fingerprints in the distribution of light from gravitationally lensed galaxies. The number and distribution of these subhalos is actually a test of dark matter theories. Different types of dark matter predict different amounts of small-scale structure. If dark matter is cold and heavy, it should form many small subhalos. If it is warmer and lighter, the subhalos should be smoothed out and less common. By counting the subhalos around the Milky Way and other galaxies, we can learn about the properties of dark matter particles. This is active research right now. The Gaia Space Telescope, which has been mapping the positions and motions of over 1 billion stars in the Milky Way, is providing unprecedented data for this kind of study. The streams of stars that crisscross our galaxy record the gravitational history of every object they have passed. By analyzing these streams, astronomers are searching for the signatures of dark subhalos. Some preliminary results suggest there might be fewer subhalos than the simplest dark matter models predict. This could mean that dark matter is not quite as cold as we thought, or that it has some self-interaction that smooths out the smallest structures. Or it could mean that our observational techniques are not yet sensitive enough to detect all the subhalos. The jury is still out. I want to spend some time on a topic that often confuses people: the relationship between dark matter and black holes. Black holes are regions of space where gravity is so strong that nothing can escape, not even light. They form when massive stars collapse at the end of their lives, or when matter accumulates in the centers of galaxies. Black holes are called black because they emit no light, hence the name. So, are black holes the same as dark matter? No. They are different things entirely. Black holes are made of ordinary matter that has been compressed to extreme density. When a star collapses into a black hole, the matter that made up the star is still there. It is just concentrated in an incredibly small space. The protons and neutrons that once fused hydrogen into helium in the star's core are still present, crushed into a singularity at the center of the black hole. Dark matter, by contrast, is not made of ordinary matter at all. It is composed of particles that do not interact with light and may not be made of protons or neutrons or anything we find in ordinary atoms. Dark matter is distributed throughout the universe, forming vast halos around galaxies. Black holes are localized objects concentrated at specific points. There is one interesting connection between black holes and dark matter, though. Some scientists have proposed that dark matter might consist of primordial black holes that formed in the very early universe, long before stars existed. In the first fraction of a second after the Big Bang, the universe was an incredibly hot, dense soup of matter and energy. If there were regions where the density was slightly higher than average, these regions might have collapsed directly into black holes. These primordial black holes could have any mass, from less than an atom to more than a mountain, depending on the exact conditions when they formed. If primordial black holes exist and have the right masses, they could potentially explain dark matter. They would be invisible. They would interact only through gravity, and they would clump together in the halos of galaxies. They would be dark matter that is actually black holes. For many years, this idea seemed to be ruled out. Observations placed limits on how many primordial black holes could exist at various masses. There could not be too many small ones because they would have evaporated by now through Hawking radiation. There could not be too many big ones because they would disrupt binary star systems or produce too much gravitational lensing. The allowed window seemed too narrow to account for all the dark matter. But in 2016, something changed. The LIGO experiment detected gravitational waves from two merging black holes, each about 30 times the mass of the Sun. These were surprisingly heavy black holes, heavier than most astrophysical models predicted. Some researchers suggested they might be primordial. Since then, interest in primordial black holes as dark matter has been revived. New theoretical models have found ways to produce primordial black holes with the right properties. New observational techniques are being developed to search for them. The idea is back in play. Whether primordial black holes actually make up dark matter remains to be seen. But it is a reminder that the answer to the dark matter puzzle might come from an unexpected direction. Let me tell you about some of the best laboratories we have for studying dark matter dwarf galaxies. Dwarf galaxies are small galaxies, containing anywhere from a few thousand to a few billion stars. Compare this to the Milky Way, which contains roughly 200 billion to 400 billion stars. Dwarf galaxies are the most common type of galaxy in the universe, but they are hard to see because they are so faint. What makes dwarf galaxies special for dark matter research is their composition. Many dwarf galaxies are almost entirely dark matter. The ratio of dark matter to ordinary matter in these galaxies can be hundreds to one or even higher. In some extreme cases, dark matter outweighs the stars by a factor of 1,000. This makes dwarf galaxies remarkably clean laboratories. In a large galaxy like the Milky Way, the complex interplay between ordinary matter, stars, gas, supernova explosions, and black hole activity makes it difficult to isolate the effects of dark matter. In dwarf galaxies, there is almost nothing but dark matter. The handful of stars present are just traces, allowing us to measure the dark matter's gravitational influence. The Milky Way is surrounded by dozens of known dwarf galaxies. Some are relatively large, like the Large and Small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere. Others are much smaller and fainter, discovered only in the past 2 decades by careful surveys of the sky. These faint dwarf galaxies are incredibly dark matter dominated. Segway 1, discovered in 2006, contains only about 1,000 stars spread across a region about 100 light-years in diameter. Yet the stars are moving faster than they should be if the only gravity came from the visible stars. The motions imply a dark matter mass of about 600,000 times the mass of our star. That means dark matter outweighs visible matter by a factor of nearly 1,000. Studying these dwarf galaxies can tell us about the properties of dark matter. If dark matter particles can annihilate or decay, the products might be detectable as gamma rays coming from the centers of dwarf galaxies where the dark matter is densest. The Fermi Space Telescope has spent years searching for such signals. So far, no convincing detection has been made, but the limits are becoming increasingly stringent. The distribution of dark matter within dwarf galaxies is also informative. Different dark matter models predict different density profiles. If dark matter is perfectly cold and collisionless, simulations predict that halos should have dense cores. But some observations suggest the cores are less dense than expected, possibly indicating that dark matter has some self-interaction or other properties we have not accounted for. This discrepancy, sometimes called the core cusp problem, remains an active area of research. It could indicate new physics about dark matter, or it could reflect our incomplete understanding of how ordinary matter affects dark matter distributions. The answer is not yet clear. Let me talk about one of the most precise pieces of evidence for dark matter, the cosmic microwave background. The cosmic microwave background, or CMB, is light left over from the early universe. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this happened, the universe was opaque because free electrons scattered photons in every direction. After this happened, the photons were free to travel unimpeded through space. Those photons have been traveling ever since. We detect them today as a faint glow of microwave radiation coming from every direction in the sky. This glow has been measured with extraordinary precision by satellites like COBE, WMAP, and Planck. The CMB is not perfectly uniform. There are tiny variations in its temperature from one direction to another, fluctuations of about 1 part in 100,000. These fluctuations are the imprint of the density variations in the early universe, the seeds that would later grow into galaxies and clusters. The pattern of these fluctuations depends on the composition of the universe. Different amounts of ordinary matter, dark matter, and dark energy produce different patterns. By analyzing the CMB in detail, scientists can measure the amounts of each component with remarkable accuracy. The Planck satellite, which operated from 2009 to 2013, produced the most precise measurements of the CMB ever made. Its data tell us that the universe is about 68% dark energy, about 27% dark matter, and about 5% ordinary matter. These numbers are not guesses. They are derived from careful fits to the data, with uncertainties of only a few percent. The CMB also tells us that dark matter was present in the early universe. If dark matter did not exist, the pattern of fluctuations would look different. The peaks and troughs in the CMB power spectrum, the mathematical representation of the fluctuations, occur at specific positions that depend on the amount of dark matter. The observed positions match dark matter predictions perfectly. This is powerful evidence that dark matter is real and has been part of the universe since the beginning. It is not something that developed later after galaxies formed. It was there from the start, shaping the universe from its earliest moments. As we near the end of this exploration, let me step back and consider what we have learned. Dark matter is real. The evidence comes from multiple independent sources: galaxy rotation curves, galaxy clusters, gravitational lensing, the cosmic microwave background, the formation of large-scale structure, the bullet cluster. Each piece of evidence on its own might admit alternative explanations. Together, they form a coherent picture that is hard to explain without dark matter. Dark matter is not made of ordinary atoms. Searches for MACOs and other dark ordinary matter have come up empty. The CMB independently confirms that baryonic matter makes up only a small fraction of the cosmic inventory. The dark matter must be composed of particles not found in the periodic table. Dark matter interacts very weakly, if at all, with ordinary matter and light. Decades of direct detection experiments have not found a signal. This tells us that dark matter particles, if they exist, must interact much more rarely than even the weak nuclear force would suggest. Dark matter shapes the universe. It provided the gravitational template on which galaxies formed. It holds galaxies and clusters together today. It determines the structure of the cosmic web. And dark matter remains mysterious. Despite nearly a century of research, we do not know what it is made of. We have candidates and theories, but no confirmed detection. The particle or particles that compose dark matter are still unknown. This is the state of knowledge as of now. The mystery is unsolved, but the search continues. What can you take away from all of this? Perhaps the most important lesson is that the universe is stranger than it appears. What you can see is not all there is. The visible cosmos, as beautiful and vast as it seems, is just a small fraction of reality. Most of what exists is hidden from our eyes. This should not be frightening. It should be inspiring. There are discoveries still to be made, secrets still to be uncovered, wonders still to be found. The universe is not a closed book. It is an open frontier. Dark matter also reminds us of the power of human reason. We discovered something invisible by watching how visible things move. We mapped it by measuring how light bends around it. We quantified it by studying the echoes of the Big Bang. Our instruments and our minds have reached beyond our senses, revealing a hidden world that no eye has ever seen. There will come a day when we understand dark matter. Maybe it will be WIMPs after all, detected in the next generation of underground experiments. Maybe it will be axions, singing their faint song in a magnetic field. Maybe it will be something no one has thought of yet, a particle or a phenomenon that exists only in the imaginations of scientists not yet born. Until that day, we will keep searching. We will build new experiments and launch new telescopes. We will propose new theories and test old ones. We will chase this invisible quarry through the dark reaches of the cosmos, knowing that the hunt itself is worthwhile, that the search for truth is its own reward. Dark matter is out there. It is in the space around you, in the halo of the Milky Way, in the vast voids between the galaxies that dot our universe. It is everywhere and nowhere, invisible and immense, the hidden architecture of everything we know, and one day we will understand it. Let me close with a final observation. Look up at the night sky on a clear evening. You will see stars scattered across the darkness. You might see the band of the Milky Way if you are far from city lights. You might see planets, and maybe even the faint smudge of Andromeda, our nearest galactic neighbor. Everything you see up there is just 5% of reality. The dark spaces between the stars are not empty. They are full of something you cannot perceive, something that does not shine, something that has been there since the universe was young. You are looking at the tip of an invisible iceberg. The universe you see is floating on a sea of dark matter, held together by forces you cannot feel, shaped by masses you cannot detect. This is humbling, but it is also magnificent. We are tiny creatures on a small planet, orbiting an ordinary star in an unremarkable corner of a single galaxy among trillions. And yet we have figured out that the universe is mostly invisible. We have measured the unmeasurable. We have weighed the unseen. That is extraordinary. Dark matter is one of the great mysteries of our time. Solving it will require new ideas, new experiments, and perhaps new physics. The answer may be decades away. It may be centuries away. It may be forever beyond our reach. But whatever happens, we have already accomplished something remarkable. We have glimpsed the hidden universe. We have proven that reality extends far beyond what we can see. We have learned to trust the evidence even when our senses fail us. Dark matter is the invisible universe that controls everything. It is the hidden hand shaping the galaxies. It is the secret structure of the cosmos. And for now, it remains a mystery. But mysteries are meant to be solved. Thank you for joining me on this journey through the dark. The universe is vast and strange and full of wonders. Dark matter is one of them. Until next time, keep looking up. Keep wondering about the invisible forces that shape our universe. And remember, what you see is not all there is. The cosmos holds secrets we have only begun to uncover, mysteries written in gravity rather than light. Dark matter is just one chapter in a story that is still being written